think I'm streaming. It's very slow on this side. Okay, I am. There's like a lag. Okay. Okay, so do you both want to stay, or is one of you gonna leave?
I can stay because
Okay.
Do you want to? I just want to give you like this 1 hour off, but if you want to, I can leave, so I don't mind it.
I mean, like, it's fine. We can just both stay here.
Or Ilkin, if you want to leave, that's fine. It's fine.
Yeah, I can just want to, just every week, like, one TA takes 1 hour off, but yeah, I can do it.
Okay. Whichever you decide. I'm okay with either.
Yeah, well,
Okay. So let's do some math. We don't have a lot of people today, I feel like. Okay. So today we're going to talk about Boolean algebra, relations, functions, all the fun stuff. Okay. So the first one. My computer is doing weird things. In order to prove De Morgan's law, we have to prove the following two statements. First of all, can someone explain to me why that is true? Why do you think that is true? Why is it that in order to prove De Morgan's law, which is this thing up here, we need to prove the two statements down there? Any ideas? Okay, so basically, if we look here, we have this A times B complement, or like A intersect B complement, right? So we want to show that the AB complement is equal to this thing on the right side. So then if we kind of draw a Venn diagram, if we use like set notation type of thing, kind of, we have A, B. So this right here is A intersect B. And then if we have a U set, this is the U, right? So then the complement is everything other than the shaded part. Right? So then we want to show that the shaded part, the everything other than the shaded part, the white part, is equal to the thing on the right side. So that means, so that gives us this thing, which is the shaded part, add up with whatever that's the white part, should give us the entire set U. Does that make sense? That's why we have this one right here. So we kind of have to show that AB right here and then the right side is a partition of the entire set. That gives us that the complement would be the same as this. I don't know if that makes sense. But like you can draw a Venn diagram and then try to figure it out. It shouldn't be too hard, actually, if you just draw a few circles. But let's do the proof. Any idea how to start? Let me write this down again. A times B plus. So that's the first one. Yep. Any ideas on how to start? I think Boolean algebra is a little weird. What can we do? Okay, so we're going to start with So in order to be very, very precise, let's start with commutative. We're going to switch these two, the orders of these two. We're going to do this. Okay, so that's commutative. Does that help? What do we do next? What can we do? Notice that we have a plus and a multiply.
Would that be like a law of complements or something like that?
So you mean this one?
Or yeah, well, anything plus the complement of itself would be 1. But what's the rule for that?
Anything plus the complement would be
Like a plus a complement is equal to 1.
right, but where do we have that? That is true, but where do we have that now, or what do we do now? So
I
that
think-
is something that we're going to do later on, but how do we get there?
I don't know.
Right. Okay. So I feel like if we write this in step notation, it would be a lot easier. But basically, we have this. This is kind of the union, right? And this is the intersection inside. So when we have these two different signs, one outside the parentheses, one inside, what we can do is we do distributive. Yes, somebody said it. Somebody said that in the chat. Right. So we're going to go with A complement plus B complement plus A. So that's the first part. Times A complement plus B complement times plus B. That's the second one. That would be 1. We just considered this first part as a whole thing, and then we distributed it. So now what can we do? So now we cannot use distributive rule anymore because we all have the same signs inside. Inside of each parentheses, we have the same sign, right? So what do we do now? What can we do now? How do we get the thing that you just said? A complement plus A is 1, right? But how do we get there?
You could, or on the left part of the equation, you could add a and a complement, and you could add b and b complement in the second part.
What do you mean add?
I
Like,
mean, there,
But
so
if
if
you can't add things without subtracting them, right?
I mean, if you have a complement plus b complement plus a, couldn't you just do a complement plus a plus b complement?
Yes, exactly, right? So we're going to do, it's more like, yeah, commutative, and then we're going to use associative. Right, okay, so we're going to switch them around. We have b complement plus a complement plus a, right? We just did commutative. And then we're going to do, this one doesn't change. This is 1. So this is exactly what you just said. And then we're going to use the associative law. Oh, actually, I feel like I shouldn't be writing. Anyway, I feel like we shouldn't be writing this is equal to 1 on the right. We should just do this instead. That's better. So that's the associative. Okay. So now what do we do? Same thing that you said before. What is this?
That'd be b complement plus 1.
Yes, b complement plus 1. Yep, exactly. And then this side is what?
And that'd be a complement plus 1.
Yep, a complement plus 1. What rule did we use? We used negation. So what do we do now? what is a B complement plus 1? Something union the universal set. What is that? That would just be 1, right? Intersect with 1 times 1. So that's based on universal bound. And what is 1 times 1?
1.
Yes. And that's based on identity. Does that make sense? Okay. We're going to move on to the second one, which is to prove A times B times A complement plus B complement is 0. So this is basically saying that these two sets, if you think about in set notation, they do not have an intersection. Their intersection is empty. So very similar, right? What do we do now?
Distributive to start
Yep.
with.
Mm-hmm. Exactly. So A times B times A prime, A complement plus A times B times B complement, right? Or let's write like this. It's a little bit better. Distributive. Okay. And now, similarly, we're going to do commutative. Right? We have B times A complement plus A times B complement. So that is commutative. Very similar to what we've done before. What do we do now?
Negation.
Almost, very close. But first of all, we have to use associative, right? So we have B times, so basically move the parentheses around. And now, what is A times A complement?
0.
Yes, exactly. So we have this, right? Plus the same thing here. What rule did we use? That's negation again. And then, what do we have?
Universal bound.
Yes, universal bound, and what do we get?
0.
Yes, so 0 plus 0, that would be universal bound. Anything intersect with the empty set is always empty, right? I mean, and that would be 0 by identity. Any questions? I really think this would be a lot easier if we had set notation or logic notation. It's just the signs are a little weird.
Can you explain one more time why we went through all of this to prove De Morgan's?
Right. So we're trying to show that these two, so like if we think about set notation, we're trying to prove that this right here, so these two things, if we're thinking about them as sets, right, this is an intersection, right? So we want to show that these two have 0 intersections, so empty intersections. We want these two to be empty. And then we want also these two things to add up together to become the whole set. So basically we're saying that if this is the universal set, I'm just gonna like draw this. So this part is this A times B. So this is A intersect B. Then the right side would be this thing on the right. A complement plus B complement. This is on the right side. So this is a universal set, right? So what does the De Morgan's law say? The De Morgan's law say that the complement of this side is the right side, right? The complement of the left is the right. So if we show that they don't have an intersection and the union of them is the universal set, that shows that these two partition the universal set. And that gives us exactly the complement of the left is the right. That's exactly what the De Morgan's law says.
Okay, that makes sense. Thank you.
Yeah. I think that's the hardest part of this proof, honestly. Okay, this one shouldn't be too hard. Draw the two-set arrow diagram for the relation described below. The power set is the domain. The power set of this set is the domain, and then the set B is the codomain. The rule is that Sn in R means that n is a sum of the elements in S. So where do we start? Let's start with the domain. Can someone give me all the elements in the power set of the set? What's the first thing?
The empty set.
Yep, the empty set. And then what do we have? The single element ones? 1, 2, 4, and 8. I'm going to have to write very small because I think I'll run out of space. And then the 2 element ones, 1, 2, 1, 4, 1, 8, 2, 4, 2, 8. Ugh, I'm definitely going to run out of space. 4, 8. Three element ones. 1, 2, 4. What do I do now? This is not good. Okay. 1, 2, 4. 1, 2, 8. 2, 4, 8. Is that all? 3 of them? No, there's one more, actually. 1, 2, 8. 1, 4, 8. 2, 4, 8. Okay, and then the last one. 1, 2, 4, 8. If you have more space on your notebook or wherever you're writing on, that would be better to write them all vertically, because this would be a little hard. And then the domain, the codomain. What is the codomain? The set B, right? So it's 0, 1, 2. Okay, let's actually write it like this. They would all line up. Okay, so how do we draw the arrow? Where does this one go to? The empty set. Where does the empty set go to? So it means the sum, right? Go ahead.
It wouldn't go to anything.
what is the sum of the elements in the empty set?
0.
Yes, because there's nothing, right? So it's going to go to 0. What about 1?
To 1.
Yep. And 2 goes to 2, and then 4 goes to 4, right? And then 8 goes to 8. Okay, what's 1, 2? Where does 1, 2 go to?
3.
Yep. 3, and then 1, 4.
Goes to 5.
Yep. And then 9, and then 10. 1, 2, 4.
7.
Yep. 7. And then 1, 2, 8.
11.
11. 1, 4, 8.
13.
13. 2, 4, 8.
14.
And then, oh, I missed this one. This goes to 12. And this one, last one goes to 15. Right? 1, 2, 4, 8 goes to 15. I hope you have a better diagram than this one. Write them vertically. Should look a little prettier. Does this make sense? Any questions? Okay. Oh, I should have done that anyway. Another arrow diagram and composition problem. Let C be from the power set of xyz to the power set of xyz, be a function with the rule C of A is equal to the set minus A. And let N be this set, be a function such that N of A is the number of element in A. This is the function. Which composition is defined out of these two? Which composition would be defined? How would we know that? Any ideas? How would we know which composition is defined here? So if we want a composition, right? So like, think about it like this. If we have C of N, so C composed with N, then this means this is a function that basically goes from domain of N to codomain of C. Okay, and then the other one is the domain of C goes to codomain of N. So the inside one gets unpacked first. So we look here, we know that C is from the power set to the power set, and N is from the power set to another set. So basically, if we want a composition, then the output, so the codomain of the first function needs to become the domain of the second function. So what I'm saying is that, let's say if it's this case, then we have domain of C goes to codomain of C goes to codomain of N. And this becomes of N. So basically what I'm saying is that the codomain of C, the codomain of the first function we unpack, needs to be the same as the domain of the second function. So if we look at C and N, which one has to go first? So I'm saying, so there's it's like map to the codomain of C. I don't know if this makes any sense, but basically what I'm saying is that the codomain of one function needs to be the same as the domain of the other function, right? So C has to go first. C has to be the function. Then we have this codomain right here, which is the same as the domain of the second function. If we do the other way around, the codomain of N is this 0, 1, 2, 3 set, which is not the domain of C, so we cannot compose these two functions. Does that make sense? Any questions about that? So that's why C has to go first. So we have the composition. So this is defined. The composition notation is a little weird. It's backwards. So whatever is written on the rightmost side gets unpacked first. Any questions about this? Okay, so how do we draw the arrow diagram? We have N of C. How do we draw the arrow diagram? So C is the power set, is a function from the power set of XYZ to the power set of XYZ. And it is defined as C of A is equal to XYZ minus A. So first of all, what is the domain? Power set of XYZ. First thing is also empty set.
X, Y, and Z,
Yep.
and X, Y, and XZ, and then YZ, and then the 3 altogether.
Awesome. Right, and then we have the same thing on the right side. X, Y. So how does the diagram go? Where does X go to? So basically now X is the set A, right? And then C of A means XYZ minus A.
X would go to YZ.
Yep. X would go to YZ. Y would go to?
XZ.
Yes. And we forgot the empty set. Where does the empty set go to?
The empty set. Or no, XYZ.
Yes. Empty set goes to XYZ. So we keep going. Z goes to XY. XY goes to Z. XZ goes to Y. YZ goes to X. Right? So basically, it's just flipped over. Okay, and then now we have 0, 1, 2, 3 as the codomain, and then we define N to be the number of elements in A. Okay, so A, remember A are these sets on the left, okay? These are A's on the left. You have 0, 1, 2, 3. Okay, so where does the first one go? Remember, A is this set for the first one, for the empty set here. Wait, actually, Yeah, but then, okay, so we're gonna look at the composition, right? So n here, we're gonna plug in this column first. Plug in this column, 0, empty set would have 0 element in it. X, Y, Z would have 1 element in it. And then X, Y would have 2. X, Z would have 2. Y, Z would have 2. And then X, Y, Z would have 3. So that is the second function from this one to this one. That is n, and that is c. Can someone mute their mic? Okay, so what happens now? What does the function actually look like in the end? What is c? What is n composed with c? So that function would be going from the domain of c to the codomain of n, right? So basically what we do is to connect the two arrows to find one arrow. So for example, the empty set goes to the last one to 3, right? So then in the new graph, in the new arrow graph, we're gonna have the empty set directly go to 3 for the composite function. And we're gonna have x go to yz, right? And then it goes to 2. So in the new diagram, we would have x directly goes to 2, maps to 2 for the composite function. Any questions about that? Does that make sense? So we basically have this double arrow for a composite function. I don't know what's happening with Zoom today. Can you still hear me, actually?
Yes.
Okay, this is really weird. My computer is doing some weird things. But anyway, let's keep going. And until I get cut off at some point, I might. Okay, the next problem. Consider the relation R on the set A with the rule that X relation R is if X minus Y is divisible by 3. Draw the one set arrow diagram for R and R of R and describe the latter relationship with an English sentence. Let's do the first part, draw on one arrow diagram of R, right? Okay, so I'm just gonna write 1, 2, 3, 0, 1, 2, 3, 4, 5, 6. Okay, so how does it go? X minus Y is divisible by 3. Also remember the negative ones. -3 is also divisible by 3. But what's the first thing? Also, 0 is divisible by 3, right? So the first thing we notice is that we have an arrow. Each element has an arrow goes back to itself because 0 minus 0 is 0, right? 1 minus 0 is also 0. 1 minus 1 is also 0. 2 minus 2 is also 0. And 0 is divisible by 3. So we have an arrow going back to itself for each element. So that's the first thing. So now let's consider all the other options, right? When the two elements are different. So 3 minus 0 is 3. 0 minus 3 is -3. That's also divisible by 3, right? So we have arrows going this way, arrow going that way. Same thing applies to 4, 1, right? 5, 2, 6, 3, right? What else? There's one or like 2 last ones.
Six minus 0.
Yep, 6 minus 0 and 0 minus 6, right? Both 6 and negative 6 are divisible by 3. So what would R compose? So this is R, right? This is R right here. What would R composed with R look like? Remember what we did before, that some like a composition of a relation or a function would just be double arrows. So we have the first function needs to satisfy the R on the inside. The first arrow needs to satisfy the R on the inside, and the second arrow would satisfy the R on the outside. So think about it like this. If we have, do we have 0, 0, 0 in R composed with R? Does 0, 0, is 0, 0 in R composed with R? It is, right? Because we just go through it twice. We start from 0, we go back to 0, and we go back to 0 again. We loop through it twice. That's a double arrow. We have 2 arrows here. That's why 0, 0 is also in R composed with R. So if that's the case, any of these single ones, these like going back to itself arrows, these relations, these things would all be in R composed with R. So what about, let's say, 0 to 3 and 3 to 0? Is that inside of R composed with R?
You could have 0 to 0 and then 0 to 3.
Yep, exactly. That's how it goes. Yep, you can have 0 to 0 and 0 to 3, or 3 to 0 and 0 to 0, right? Or the other way around, 3 to 3 and 3 to 0. Any type of double composition would give you, if that satisfies, then we have that element is in R composed with R. Okay, so if that's the case, then we have all of the double ones too. So that means that this diagram right here is also the diagram for R of R. Any questions about that? Okay, so how do we write an English sentence for R of R? So basically we're saying XY in R of R means what? It's just a definition. Means there exists Z such that XZ is in R and ZY is in R. And then how do we write these in English sentences? So we're gonna keep going one more step. So it means that there exists Z such that we substitute whatever the relationship means. The relationship means X minus Y is divisible by 3, right? So such that X minus Z is divisible by 3 and Z minus Y is divisible by 3. I didn't write the divisible completely. You can do that. Does that make sense? Any questions about this? Okay, I think we can do this one quickly. So let A be the set of all students at your school, B be the set of all sections of courses. So let's write them down. A, all students. B, all sections of all courses. C, all instructors. So if X, Y in R means that student X is enrolled in course Y, and A, B, and S means course A is taught this semester by instructor B, what is the meaning of the relation S of R? So we start with something like Mn in S of R. What does this mean? Just use the definition. What does this mean? We want a transitional element here. If Mn is in S of R, means that there exists, let's say, what can we use? D, let's use D. There exists D such that MD is in R and DN is in S. So how do we write these things in words then? MD in R means what? Use the definition of these relationships up here.
The student is in a course.
Yes, exactly. So that means that student M is enrolled in course D. Okay, so the next one, DN is an S. Means what? So up here.
It means that course D is being taught by instructor N.
Yep, exactly. Course D is being taught by instructor N. So how do we put them together? What does MN in SR, S composed of R, mean in English? How do we put these two sentences together?
It means that student M is in a course being taught by instructor N.
Yes, almost. Student M is enrolled. Sure, that's fine. Actually, we don't need to actually mention the transitional element in the final. So yes, you're right. Student M is enrolled in a course taught by instructor N. Any questions? Okay, if you have no questions, we can we have 5 minutes. Let's see. Oh, this one should be very hard because we did very similar things before. So prove that this function is one-to-one and onto. First of all, we'll write it. Prove. So how do we prove one-to-one? What do we do? How do we prove one-to-one?
We check that each element maps to only one element in the codomain that knows two domain values map to one codomain.
Yep, that's exactly what one-to-one means. So what we're going to do is to say, so this is how basically all one-to-one type of proof starts. So let x1, x2 in R be given such that f of x1 is equal to f of x2. And then what you want to show is that x1 is always x2. x1 is equal to x2. That's a one-to-one function. So what is the f of x1? What is f of x1 in with this function, with the rule of this function? So we plug in x1. We get this on the left side, right? And on the right, we're going to have x2 cubed minus 2. So let's do some algebra now. x1 cubed basically is x2 cubed if we plus 2 on both sides. So that gives us x1 is equal to x2. Just an algebra review, when this is happening, that doesn't give you the same conclusion. The odd ones, the odd powers give us this conclusion. The even ones don't. Okay, so then we've proven that when fx1 is equal to fx2, x1 is always equal to x2. So that means, therefore, f is 1-to-1. All right, how do we prove onto? What does onto mean? It means that every element in the codomain has a corresponding element in the domain, right? So we're going to start an onto proof with let y in R be given such that y is equal to x cubed minus 2. So now what we can do is just to solve for x. So we need to show that there's always an x that's in R that map to this y. Does that make sense? So then that's how we prove that every y in R in the codomain has a corresponding x. So we're going to solve for x. We have y plus 2 is equal to x cubed. And then we just take the cube root, right? So there's one last step we need to do before we can conclude that this function is onto. We need to show that x is actually in the domain of the function. So we need to show that x is actually in R. But that's simple, right? We just need to show that this part is in R. And that's definitely in R by closure of R under basically everything. So I'm just not going to write this. I'm just going to say by closure of R, this part right here is in R. So X is in the real numbers. Now we can conclude this function is onto. And then you can say that this function is one-to-one and onto. And the inverse function, we already found it, is basically this one. So f inverse of y. So inverse is just a flipping x and y axes. So that would be our inverse function. Any questions about this?
Does a function being one-to-one imply that it is onto?
No, it does not, because we can have functions like this, right? So if this is the domain, let's say this is the domain codomain, right? So we can have something that looks like this, right? We have 4 elements in the codomain, and we have 3 in the domain. And this is a one-to-one function. Every distinct element is mapped to a distinct element in the codomain, right? That's one-to-one, right? But then because we have this extra here, that element in the codomain does not have a corresponding X.
Gotcha. Thank you.
Make sense? Yes. So let me think. A simple example is like, y is equal to x squared. If we say that this function goes from R to R, then, if you draw, it looks like this, right? So every x has a corresponding y, but this is not a one-to-one function. But this is definitely also not an onto function if we say that the codomain is R, because the negative ones don't get any, they don't have anything corresponding to them. They don't have any X. So this is neither one-to-one or onto. Probably not the best example, but does that make sense? Okay, any more questions? If not, then I think that's time. Okay, no more questions. All right, then we'll finish here, and good luck on, I think homework 3 is due on Friday. Come to office hours if you have any questions. And have a good rest of your Thursday. It's Thursday today, right?
Thank you.
No problem.
Hey, do you want to stop live on YouTube?
Yeah, I'm trying, but my Zoom is acting so weird. I literally don't get any, I can't. Oh my God.
Is it because you're I don't know, both share screen and at the same time live on stream, just make it slow?
Maybe. Wait, but I'm sharing screen on another computer.
Okay.
Yeah. Yeah, and then, I don't understand what's happening. Okay, can I just stop this somehow?
Or do you want to leave the meeting, or is that stop live?
Go to you. My Zoom is stuck. I don't know what to do. Let me just force stop it real quick. Zoe, can you stop streaming since you're the host now?